This is Chapter 10, Problem 1. And it says, a ball is thrown horizontally from a cliff at a speed of 10 meters per second. What is the speed 1 second later? Well, in the horizontal, 1 second later, it would be still 10 meters per second. But now it has added speed in the vertical, which we have to determine. So in the horizontal, I think I just call it here horizontal v. That is 10 meters per second. Because usually, as usual in these problems, they neglect air resistance, and then in the horizontal, because there's no additional acceleration, it keeps that velocity. In the vertical, because it was thrown horizontally, initially it was 0, but now 1 second later, that would be, as it's falling, g, which is 10 meters per second squared, times 1 second comes out to 10 meters per second. So of course the second, one of the seconds cancels or divides. So now the ball is moving this way, and if we did vectors carefully, it would look something like this here. There we go. This here would be the component in the horizontal. This here would be the component in the vertical. They are of equal size, and when we put them together, we come up with this one here, and this I didn't mean to have it that thick. And because we have a 45-degree angle, we could just multiply with the square root of 2. We know that, or we use the Pythagorean theorem properly, and it would be the square root of 10 meters per second squared plus 10 meters per second squared, because they're the same. That's why I said 45-degree angle, and we could instead multiply by the square root of 2 by 1.4. And when you do that, you come up with 100 plus 100. You take the square root of 100, and that is square root of 200. You come up with 14 meters per second. The units would be meters squared per second squared, which you add meters squared per second squared, take the square root, you also get rid of the square, so the unit as well, of course, is meters per second. The next problem is Chapter 10, Problem 3. I'm going to move this a little bit over. There we go. And it says, a cannonball shot with an initial velocity of 141 meters per second. I think we can guess why they chose that number. At an angle of 45 degrees, follows a parabolic path and hits a balloon at the top of its trajectory, neglecting air resistance. How fast is the cannonball going when it hits the balloon? So the balloon, I think I would have to draw that. Let's see what color. Orange balloon. There it is. And it's at the top of the trajectory. There we go. There's the orange balloon at the top of the trajectory. Well, we have to look at that the original velocity is a 45-degree angle. And again, my thick arrow here. And this one here would be 141 meters. And now I need to split it up into its components. So the horizontal component looks like this. And the vertical component looks like that. And we would know how much that is, because it's at a 45-degree angle. All we need to do is divide the total speed by the square root of 2. and that gives us the horizontal velocity as well as the vertical velocity at 100 meters per second as we divide by 1.41. So now, as it reaches the highest point, its speed is totally in the horizontal, 100 meters per second, and at the highest point the vertical velocity is 0. So at that point it's kind of stationary as far as the vertical is concerned, and we noticed that before an object at the peak of its trajectory has a vertical velocity of 0. Of course it's still accelerating because otherwise it wouldn't fall down, and of course it does fall down. On the way up it's decelerating, on the way down it's accelerating due to gravity. So here we just have left the horizontal velocity, so its speed is 100 meters per second horizontally. Chapter 10, problem 9, which says the moon is about 3.8 times 10 to the 5th kilometers from the Earth. Find its average orbital speed about the Earth. So it says that its radius, its orbital radius, is 380,000 kilometers. 3.8 times 10 to the 5th kilometers, or roughly 240,000 miles. One way of doing this, and this is the way they want us to do, is to look at what kind of forces are acting on the moon. Well, of course, the gravitational force. I keep using that long arrow. And the gravitational force is G times the mass of the moon. This would be the symbol, times the mass of the Earth, divide by the distance squared, or orbital radius squared, and that equals mass times acceleration, Newton's second law. So mass times acceleration, but it's orbiting in a near circle, so the acceleration that we actually have is a centripetal acceleration, and the force that the gravitational force applies is the centripetal force, which we do know, v squared over r, respectively m times v squared over r. This one here is the mass of the moving object, which is the moon, or the object of interest, which means that the mass of the moon is inconsequential. And what that means is that when you put another object at the distance of what the moon is, that other object would orbit with the same velocity. One of the radius is canceling out. Here we have an r squared, and here we have an r, so this is the way I do it. I just get rid of the square here, and here I get rid of the r. And then what I get is, on the left hand side, g times the mass of the Earth divided by the radius. On the right hand side I get velocity squared, but I take the square root to get rid of the square, and there it is. And then I go to the graphing calculator, and it says take the square root of 6.67, 10 to the negative 11. It's a gravitational constant that I look up in the book, times 6, or 5.98, 10 to the 24, that's the mass of the Earth. Divide that by the orbital radius, 3.8 times 10 to the 5th kilometers, but I need that in base units, so instead of 380,000 I need 380 millions. So there we go, close the parentheses, 3.8 e to the 10 to the 8th, and there it is, 1,000 meters per second. And with the correct conversion units, you can see that this comes out to 3,600 kilometers per hour, divided by 1.6, 2,200 miles per hour.